If not, thanks, George. So next we have Triton for All, Triton as a device-independent language.
This is great. Can folks hear me? Yeah, okay, that's good. This is the clicker here. Nice. Zoom in and out. Okay, how's everybody doing? Good? Sinking in your lunch comas? So I'm Ian Bearman. I'm a dev manager at Microsoft. And I'm going to talk a little bit about not a specific code gen target, because we're hearing a lot about those today, but I'm going to with each other to play nice. It's a plugin model. Our friends at Intel have already integrated something into Triton to get started on that. So we're on our way there. What else? Well, a language isn't a language without a definition, right? So the Triton language today has some really good documentation, but it isn't exactly a formal specification for the language. There's a lot of semantics that aren't quite formally defined yet. So we got to work on building out those semantics, adding tests to test and validate conformance. We need to be able to understand what is the quality of a backend. How do we maintain that quality over time? What sort of systems are in place to ensure that that happens? They're not easy things to do. These are really, really hard problems. And then we've also heard from a few folks today about parts of the language that might be GPU specific or maybe specific to a particular GPU vendor. And how do we adapt the language to support different paradigms for different types of hardware without losing Triton's core value proposition of being a high performance language? So these are all really hard problems, and you're about to get a real rough transition, because when I put this slide deck together, I actually thought I had a whole hour to talk. So I covered all these points in depth, but it turns out I have 20 minutes and I want to leave some time for Q&A. So what I did is I just pulled out the part that I think is most important to me. So I've been doing code generation, in particular, but compiler architecture at Microsoft for about 2 decades now. And so that's the part of the problem that I find most interesting and I'm most passionate about, so that's what I want to talk about today. But that isn't to say the rest of these problems on the slide are not critical to the success of this project. So I hope the community can come together and folks who are passionate about these areas can help drive them to a conclusion that we can all use and grow with. So compiler architecture. When you open up your compiler textbook, maybe your Dragon book or whatnot, it's going to talk about different levels of intermediate representation used for code generation. It's going to talk about the HIR, the high-level representation, the part that's tied to the source programming language. It's going to talk about the LIR, the low-level intermediate representation that's tied to your target architecture. In between the HIR and the LIR sits this middle layer. Middle layer is not specific to a particular front end. It's not specific to a particular hardware target. Now, it isn't blind to those things. It has hooks or callbacks or ways to tune it for those specific cases, but it is a place where you can build shared analyses that can be shared across these different things. So how does that apply to Triton? So this is an architectural diagram of the Triton MLIR compiler. It's not complete, but I think it's good enough for today's talk. So we start with the Triton DSL, right? And that's going to get converted into MLIR at our entry point in the Triton dialect. We can think of this as our HIR. This is an intermediate representation that maps very closely, almost still, all right. So anyway, we go from Triton dialect, Triton GPU dialect, to the LLVM dialect. The Triton GPU dialect and beyond is kind of our low-level representation. It's very much tied to our target architecture, whether it's a GPU or an NVIDIA H100 or whatnot. So this type of design we have here is very streamlined, and it is probably the right design if you're building a compiler that's targeting 1 or 2 or maybe even 3 different hardware targets. But if you want to scale to more hardware targets, you need to build something, I think, a little bit different. So here's a proposal of a different architecture. And we're adding a middle layer between the Triton dialect and the specific hardware vendor dialect. In this particular diagram on the bottom, this is represented by the box with Linalg in it, and I'll come back to that in a second. One thing to take away from this diagram is that the middle layer isn't required. If you want to add the middle layer and utilize it for your hardware backend, you can do that. If you want to build a more streamlined code gen path where we go right from Triton to your GPU or XPU or NPU backend, you can do that. The box is labeled Linalg dialect because I think Linalg is going to be one of the key dialects we need to make this happen. And I'm going to be talking a little bit about that as we go through the slides. So first of all, what is the middle layer going to provide us? So let's just set the ground rules for this. So the middle layer is hardware agnostic. We have a lot of different folks here from a lot of different companies all working on different hardwares, and we want to be able to share code between those different hardwares. If somebody creates an optimization that can be used across different hardware targets, we should be able to put that into a place where everybody can share and use it. Furthermore, there are many folks here who work at companies where you actually have to create a compiler that targets multiple different backends. Building compilers is expensive. We don't want to have to keep rebuilding the same things over and over again. So we can build shared components that amortizes the cost. Second part of the middle layer is that it's language agnostic. So why am I talking about being language agnostic for a Triton compiler at a Triton conference? Well, the reality is a lot of us are working in companies where we already have MLIR software stacks. We would like to be able to take those and reuse them for Triton. Furthermore, MLIR provides a lot of built-in functionality that the Triton compiler stack today doesn't take advantage of. If we find an entry point into these common IRs, we can then reuse those passes inside Triton. Again, building compilers is expensive, and this can help us amortize the cost. So that's the case for the middle layer. Why am I talking about the Linalg dialect? Why do I think that's interesting? So hopefully everybody here is familiar with the MLIR concept, right? It's a framework for building compilers, in particular compiler IRs. And it comes with a bunch of IRs called dialects that are built into MLIR. So Linalg is one of those dialects. It sits high enough up the stack that most of the other built-in IRs can be derived from Linalg. So if you have Linalg, you can lower that to AFIND, and then you can lower that to other built-in targets, right? Or you can go right from Linalg to the vector dialect or whatnot. So it sits there at the top of the stack. It's currently under active development, so it's getting new features all the time. It's getting bug fixes. So this feels like a good dialect to take advantage of. So what are the technical advantages of doing so? So I think one of the key advantages when myself and my team looked at this was that Linalg is based around value semantics. So what do I mean by that? So not everybody here think is a compiler engineer, so let me just explain it real quickly. So if you think about your Triton program, you enter the program, pass it some pointers. You're going to load a value from those pointers. You're going to do some work on the value, and then you're going to store the value back into memory. So in between your load and your store, you have a value. The value is immutable. It can't be referenced by anything else. Those two things are what I mean today when I say value semantics. And so not only is that how a Triton program operates, because that's a good thing, it's actually really powerful inside a compiler if you can have a program that's using value semantics. It makes all of your transformations and analyses much easier to do. So we could take advantage of the way the Triton program is already constructed inside our IR. So that's a great foundation to build analyses and transformations. The second thing Linalg is going to provide us is that it explicitly in the IR talks about how the iteration space is walked. And what I mean by that is simply when you're doing an operation on two tensors, it's not really one operation. It's actually a bunch of little operations on the elements of those tensors. And Linalg is very explicit about how those operations happen, which again, in turn, makes the compiler's job much, much easier. It's so easy, in fact, that right out of the box, there's some really powerful optimizations you can just pull out of Linalg that are already written. Things like tilings and fusions that are right there for you to use. And if you need to do more or different stuff, it's extensible as well. So that's the case. Let's take a look at this in action a little bit. So this hopefully is recognizable. We've seen this a couple of times today. This is tutorial number 1 in the Triton documentation, the add kernel. It's not particularly interesting, but of course it does have one property that we all enjoy. It fits on a PowerPoint slide. So the first thing the Triton compiler does is it lowers this into Triton IR. So hopefully this is not new to everybody, that most people here are familiar with this, but it does some guideposts. The add kernel does 2 loads, and then at the end it does a store, and in between we get the add operation. The rest of the code down there is pointer arithmetic and mass calculation. We don't need to worry about that for this exercise. Okay, so we're going to take our Triton IR, and we are going to lower that into a middle layer. So it gets a little bit noisy here, right? As you move down the levels of IR, it gets less and less abstract, so we were more and more explicit. But we can use our guideposts again. So we have a couple of loads here. They get noisier in this case because I'm replicating the pointer calculation for each one of these. And then we have our store at the end. It looks the same. And in between, we have the Linalg dialect, right? This kernel doesn't really do anything. It just does an add. So there's only one Linalg operation here. But I want to point out a couple of things. I know this slide is hard to read. I'm going to zoom in a second. But for those of you who might be following along later, you can pause the presentation and look at it. You can see that, first of all, the Linalg operation is very noisy, right? It's just doing an add, but there's a lot there. It's operating on values. That's really important. And all that stuff that's there is explicitly explaining how the tensor is being walked to compute the add operation. So let's take a second to look deep at this. So this is the most technical part of the presentation. So if you can't follow along, that's okay. You can tune out for a minute and then it'll all be over. Also, if you would like to learn more about this, there's a lot of documentation online, videos, presentations with people who are much better at explaining things than I am. So please take a look. But this is a Linalg generic operation. Linalg is based around these generic operations. This one in particular implements matrix multiplication. Now, before you freak out, there is a Linalg.matmul operation that you can use, but it is syntactic sugar for the beast here that I have on the screen. So let's walk through what's here. So the very first part of a generic operation is a set of maps. These maps tell us how do we go from the dimensions that are involved in this operation to the individual elements within those tensors. So this is matrix multiplication. So we have I, j, and k dimensions. And we have our first input is I by k and k by j, and our output is I by j. So we're mapping the inputs, LHS and RHS, one element at a time into the body of this little payload here, which I'll talk about in a second. The second part of a generic operation is the loop annotations. So it calls these iterator types. So for matrix multiplication, our I and j loops or dimensions are parallel dimensions, and the k is a reduction dimension. Now, that may not mean everything. That may not mean anything to some of the people in the room. It may not mean a lot to everybody here. But if you worked on this sort of transformations before, you recognize that. So we already know these loops are parallel reductions. If I have an algorithm for doing loop fusion on parallel loops, I can bring it to bear here just by knowing that those dimensions are parallel. If I know how to tile a reduction dimension, I can just tile this Linalg generic. The last piece of the puzzle is the body. So every Linalg generic is going to carry a body that says this is what happens on a particular set of elements. So in this case, we get one element from the left, one from the right, one from the output. We multiply our two values, and then we sum them up to do our vector dot product. So that's it. So this is what's so powerful here, and this is why I think this can help us. This maps really, really nicely to what's going on in Triton, and it's really powerful for the compiler to take advantage of this stuff. Okay, so hopefully that whetted your appetite for this. If you are interested in this sort of thing, like this is gonna help us scale. This is the kind of thing that'll allow us to go from targeting a few targets to targeting many targets. If you'd like to take a look at the code, the first link there will take you to the code. The second link there is a discussion. After you take a look, you want to try it out. You want to tell me how amazing it is and how awesome. Please, I'm happy to hear that. If you also have some feedback on how the team and I can improve it or what the different approaches we can take, happy to hear that. To get up in public, but we want to be able to set up a way for folks to take a dependency on that, maybe get as a submodule inside Triton so you can build on top of it, updated it to the latest main and add new functionality there. All right, so thank you. Gonna run through some questions now if folks have it.
Yeah, thank you for the talk. That was very interesting. So I'm familiar with Linalg's concept, and I'm familiar. Something that is not clear to me from watching your talk is where do you plan to use Linalg for optimization? Like, is Linalg intended to model like the entire dispatch of the kernel, including the iteration space of the grid, or are you trying to use Linalg, like let's say within Triton IR, within Triton GPU IR, maybe to build some common optimization?
So I think it's probably closer to the first thing you said. So the way I envision this is it would sit in between Triton IR and whatever IR you need for your target architecture. So if that's Triton GPU, you would do that. What I'd like to see is a set of optimizations built on top of Linalg that can run after Triton IR before we dispatch out to machine-dependent dialects. Does that make sense?
I think I understand what you're saying. What's puzzling a bit to me is that Triton IR is really like modeling a single block of computation.
Yes.
And so you want to basically kind of almost raise to the entire grid. And so you're going.
Oh, I see. No, I don't see this operating across the entire grid. I don't think Triton. I mean, that would be interesting, but I think you probably want something more. Yeah, I don't know. No, I hadn't thought about that.
Right, so you're still modeling like block level computation.
That's right. Yeah, just within a single kernel. Yeah.
Okay.
Or a single instance of a kernel, I should say.
All right. Thank you.
It's a great question. That's an interesting idea. Are there other questions? I brought some with me in case folks didn't have any. I've talked to a few folks about this before the conference, and these are some of the frequently asked questions I had. So I think I'm running low on time, but I'm happy to take more questions from the audience. We have one in the back row.
There is an online.
Yeah, okay.
Sorry. Yeah, online question. Any plan or thoughts on coupling Triton to TOSA?
So one of the questions, my first one on my slide here, is Triton to Linalg raising the IR level? And I think it's not. We see a pretty good one-to-one mapping for most of the Triton instructions, like the TT or TL instructions to Linalg operations. But I think if we were looking at TOSA, we kind of would be going up a level of abstraction. TOS is probably better suited, or that sort of graph style representation for something like if we were trying to raise up from the whole grid or from a larger piece of the program, we have multiple kernels together. Yeah.
Yeah. So yeah, here. So for the first one, like arithmetically mapping,
Yep.
yes, but Triton, like the first programming model is basically tens of pointers, right?
Yes.
There's a pointer arithmetic there.
Yeah.
And then MRR Linalg is memref. So basically that's more like a second program model, block pointer. So it's a metadata description for the data. But Triton is a tensor of pointers.
Yeah, so
I
let's
was
go back.
wondering
Let's
how
go
you
back to
guys
this
map
diagram
these two
here.
things.
Yeah, that's a really good point. So this is the only thing in this entire Triton program that I would recommend we convert to Linalg. And that's the part that's already operating on values. So Triton, yes, operates on a tensor of pointers, but then there is a load operation that converts that to a value. And it's on these values in which we should use the Linalg dialect. At least that's my opinion.
So this is a mixture. Like
Yes.
Okay, I see. So the program you're showing here, the Linalg is mixing with those.
Yeah, we mixed it here with these load and store operations. Think of this as sort of outside the bounds of my talk today. I have a recommendation for this as well, which is implemented here, but I didn't want to get too much into that.
Yeah, I was thinking, why don't you just make a block pointer
Yes.
the main
Yes.
programming model?
Yes,
Yeah,
I agree.
Map to memref.
Yes.
That would take things much simpler.
Yes.
Okay.
Yes, block pointer makes these boxes much smaller. All right, cool. Thanks everybody.
Thanks, Ian. We have a break till 3 o'clock. So grab coffee. Again, coffee is on both sides of the room. Thank you.